Yeah, here, lecture note chapter 5, okay? Until until April 1. I posted very long times ago.
Maybe I downloaded it then.
Huh? I
Let me
gave
check
you,
before I
normally
download it.
I gave a 1 week,
That
okay?
was Dr. Kim. That was the one where you had it posted, but there was no PDF in there. You remember that? And so I didn't get a chance to even download it because it wasn't available. The link was there, but there was no PDF. Remember that?
Okay. All right. So all right. So I will give you until this Friday. Okay, this Friday is the 17th. Okay. 17th. Okay. Okay. All
Hey,
right.
Dr. Kim.
Yeah, I checked you. Okay.
I don't know if we'll have time for it, but on the quiz 9, I really had a little, because we kind of went fast. I had a little bit of a hard time with number 2 and number 4. I didn't know if we could maybe go over it. I know you posted a solution for it, didn't you?
I didn't yet.
Okay.
I think after TA is grading, then I will post it. Okay.
Okay, and then maybe once we get it back, maybe we could go over it just a little bit.
Right, right. If you have a question, then I will do that. Okay.
Okay, thank you.
Okay. All right. Now, okay. So today, I think we need to cover G transform and come back to rest of the chapter 3. I think in 2 weeks we have to finish it. So I think this week we have to finish the G transform. Okay. All right. So the G transform. Okay. So let me see. I will change it to the slideshow. I think everybody know about the Laplace transform. Okay, so Laplace transform for the analog system. Okay, the G transform digital system. So actually, the Laplace transform is for the continuous time signaling system, and the G transform is a discrete time signaling system. Okay, so this chapter 5 is a G transform and inverse G transform and property of G transform. And after that, we're gonna come back to the chapter 3. So I'm gonna post the around the end of the chapter 5, chapter 3-2. Okay. All right. So the procedure pretty much similar. Application for the DC Laplace transform, G transform. Okay, we're gonna start. I think this is changed to G transform, application of G transform. So this is G transform, not this Laplace transform, G transform. So this is easier to solving the difference equation. Laplace transform is the solving for the differential equation, and this is difference equation. Okay, so DLTI system is a discrete linear time invariant system. And then, most of our application for G transform is discrete system analysis, stability, solving the difference equation, and transient response of the, sign of the steady state response for the discrete time system and the digital system. Okay, and then digital signal processing and also communications. Okay, image processing and many other applications. Okay, so even digital control signal, robot control, everything control is a G in G transform. You have to understand that. Okay, so G transform is a discrete, transform from the discrete signal. So discrete signal is instead of the integration is continuous. So we use summation. So summation x of n, discrete signals x of n times g to the minus n. Okay, and then that is x of z. That's a G transform. Basically, I told you, as I told you in Laplace transform, there are the right side sequence and left side sequence and two side sequence. But in these cases, in ECEN 400, we're going to cover the unilateral, just the right side sequence. Okay, right side sequence. That's a code normally causal. Left side sequence and two side sequence is not a causal. So the causal is a right side sequence. Okay. All right. So this is an old one. Laplace transform. Laplace transform is, as you know, that T domain, time domain, continuous time signal. The T is the continuous time variable, continuous variable, and change it to S domain. That's a Laplace transform. As you know, that Laplace transform is this as a pair. And what is S? S is sigma plus j omega. We have 100 times, and sigma represents the damping factor, and then omega is a natural frequency, oscillatory. And we represent complex represent in the S plane, and then real axis is sigma. Y axis j omega. J omega is a frequency domain. Okay, so frequency domain sigma equals 0, so S equals j to j omega. That frequency domain, go to the frequency domain. So frequency domain is on the j omega axis. That is a subset of the S plane. Very similarly, if you understand, this is linearity. Okay. Very similarly, G transform is n domain, the discrete signal or system, change it to Z domain, large X of Z. So what is Z? Okay, what is Z? Okay, Z is complex variable, exactly the same as S domain, but in S domain, S is going to be rectangular or Cartesian form is in physical meaning. But in the case of G, discrete times, the G, there's a polar representation is a physical meaning. So this is gamma e to the j omega. This omega is a discrete omega, it's not like a W. So this is discrete omega, okay? So this is, as you know, that this omega is a continuous omega. This omega is, discrete omega. So discrete frequency and continuous frequency are a little different, okay? And so that this is, gamma represent the magnitude. It's actually magnitude. Magnitude represent the damping factor, and then omega is a natural frequency, very similar way. Okay, so you have to notice that omega is, and this is a phase. This is actually gamma is a magnitude, omega is a phase. So what does it mean phase? In this case, it's natural frequency. In continuous time cases, omega is this omega starting from 0. So 0 frequency to the infinity. Any frequency acceptable in continuous time case, S domain. But in the case of G domain, omega, this discrete omega, omega is angle. Angle means that in phase, complex, the domain, G plane, that omega is increased, then this is omega is increased. After that 2 pi, there's a repeat. It's a repeat. It's repeat. Okay. So this magnitude gamma is a distance from the origin to the somewhere. Okay. So if gamma equal 1, then this is 1. Distance is 1. That is a circle. We said that the unit circle. Okay, unit circle. So if gamma equal 1, that's a unit circle. That gamma equal 1, then omega is a frequency domain. Change it to frequency. The digital frequency is instead of j omega is e to the j omega. Okay, there's a frequency domain. So in analog domain, the y-axis is a frequency domain. Okay, subset of S domain. But in G plane, the unit circle is a frequency domain. Unit circle is a frequency domain, okay? So simulation from analog to the digital, that, you know, the y-axis, you know, j omega change to unit circle. Okay, that is a simulation, normally analog signal to the digital signal. Okay, so now the word G transform is a summation from n is minus infinity to infinity. X of n is a, you know, the n domain, and times G to the minus n. Okay, in the case of Laplace transform, as you know, that integration of you know, x of t and e to the minus st. Okay, e to the minus st. Instead of that, we said that G to the minus n in the discrete time G transform. Okay. Inverse G transform is a line integral. Line integral is contour integration. However, we are not going to use this guy. We're going to use a partial fraction expansion, just like you know, inverse Laplace transform. Okay, so inverse G transform, we're going to use the previous experience and using the partial fraction expansion method. Okay, and then Laplace transform is a linear operator. Integration is a linear operator. Right? So the summation of two signal is separately, you take a Laplace transform and add up. Exactly same thing. Summation is a linear operator. So suppose you know, function is added to function. So we're gonna take separately a G transform and add up together. It's the same thing. So linearity. Okay. All right. So complex domain. I told you that in the case of G transform is a polar form is a more important physical meaning. Okay. All right. So suppose we know that, you know, x of n is a 0.8 to the n use of n. That is use of n is starting from 0 to infinity here, and then, you know, we're gonna sketch inside of the range of these non-zero value from 0 to infinity. We're gonna sketch of 0.8 to the n. So n starting from 0. Okay, n start from n equal 0, 1, n equal 1, 0.8, n equal 2 is 0.6, is a continue until the n is infinity. Okay, so that this x of n is given. So what is the G transform? So G transform is, you know, the x of g, large x of g is a summation is because of use of n. You started from n equals 0 to infinity, and then inside of this range, the function is 0.8 to the n, 0.8 to the n, but power g to the minus n. Okay, so n combine these together, so 0.8 g to the minus 1 to the n. Okay, so this is same with this guy. Now, so we have a closed form. Okay, here closed form. Okay, so if you look at the closed form, summation of k from starting point to small m to the large M, ending point to large M, and b sub k is a closed form is, you know, denomination part is 1 minus b, so b here, and then numerator part is the b to the m is starting from here, starting point, small m, and minus b. The important thing is that, you know, ending point large M plus 1. So we're going to use this formula. So we're going to use this formula, okay? So this formula is actually this one is a B, okay? So this one is B. Okay. This is like a B. Okay. So this is like a B, or this is, you know, B, okay? This is B. Okay, then a denomination part is 1 minus b, so 0.8 g to the minus 1. And, you know, the numerator part is, you know, 0.8 to the g to the minus 1, starting from 0 here. So to the 0 is 1, and minus, and this one is infinity, you know, ending point is infinity, so ending point. So this is the important, okay? This part is important. Okay, so depends on this part. So 0.8 to the g to the minus 1. Okay, so magnitude is less than 1. Okay, less than 1. For example, suppose the 0.8 to the 0.8 to the n. You know, n is infinity, then this approach to 0. Okay, however, if it's greater than 1, and such as 1.2, okay, to the infinity, that is approaching to the infinity. Okay, so region of convergence, condition of region of convergence is this guy, so 0.8 g to the minus 1 must be a magnitude, okay? Magnitude is less than 1. And this is same with the 0.1 and g to the, because 0.8 is positive number. So otherwise we have to do this guy, okay? And then less than 1, then, okay, then this is g to the minus 1, g to the magnitude of g is greater than 0.8. Okay, so this is a region of convergence, ROC. Okay, if ROC, okay, so this is approaching to 0. In this condition, this is approaching 0. Okay, so far it's okay? Anybody has a question?
You're just going really fast, but it's all good.
Okay, so in this condition, region of convergence, so this is conclusion is 1 over 1 minus 0.8 g to the minus 1. Okay, in these cases, in this range, we have this is 1 over 1 minus 0.8 g to the minus 1. So this is a causal form. Okay, this is causal form. So this is causal form, but in order to find the pole and zero, okay, we may need to go to the non-causal form. So non-causal form is because this is g2 minus 1 first order system, that is every term multiplied by z. So z is z, 1 times z is z, 1 times z is z, 0.8, and g to the minus 1 times g is 0.8. So this one, okay, this is the conclusion. This is non-causal form, but even though this is non-causal form, we can find the zeros. Zero is g equals 0, and pole is at the g equals 0.8. Okay, so region of convergence is this. Okay, go ahead.
Hey, so for the region of convergence, looking at the equation in the formula given, in the denominator it's 1 minus b. So when you're doing the region of convergence, it would always be it'd always be less than 1, and then you just multiply the z over to the right side, correct?
Right. So this one is multiplied by z. Okay, if this is second order, then you need to multiply by each term g squared. Okay, but this is first order, only g to the minus 1. So each one is multiplied by z, then the g over g minus 1. That's a first order system. Okay, so one delay, only one delay. This is one delay. Okay, so that I think this is pretty much easier than Laplace transform. Okay, but summation. Only your concern is the regional convergence. Okay, regional convergence is this one. Okay, so the as you know that in the Laplace transform, without very common sense is the right side sequence. The right side sequence is the rightmost of the from the rightmost pole to the right side. You remember that, right? So, for example, in the case of in the case of Laplace transform, Laplace trans. In case of Laplace transform, suppose you have many. Come on. Okay. Suppose we have many pole here. Okay, pole. Then rightmost. Right side sequence is from the rightmost pole to the right side. That's a reasonable convergence. ROC. That's a normal way. Okay. So very similar way in G transform. Okay. In these cases, we have a pole here. So this case is okay. I think I need to erase it first. Okay. Okay, I will erase it. Okay, so now, okay, so that if you look at that, okay, if you look at this, okay, so the this is zero is circle marked as a circle, so this is origin, and then pole is marked as positive 0.8, and then the region of convergence is the magnitude of z. Magnitude of z is from origin to the distance, 0.8, and then this is represent the circle. So circle, greater than means that the exterior from the circle of 0.8, and the circle of 0.8 cannot include in the region of convergence because the pole is located here. Okay, so normally in G-transform is a exterior. Suppose we have a many pole, for example. So suppose we have a many pole here, okay, here or here. So many pole, then the gamma magnitude is high. Highest one. The highest one is the exterior from this guy. That's a similar with the Laplace transform. Okay, that's a normal way for the right side sequence because any pole should not include in the region of convergence or region of convergence. Pole means that a function go to the infinity. So pole should not include inside of region of convergence. Okay, so this is a basic understanding for the G transform. So we need to some kind of practice here. Okay. Okay, so in the case of Laplace transform continuous time case, if you have, I think you remember this guy here, then this is 1 over s plus 2, and region of convergence is greater than at the pole here. Okay, so that we can see like this. So as I explained, this is j omega axis means that sigma equals 0. S is, S equals sigma plus j omega. So sigma equals 0, then S is j omega. This is j omega. There's a frequent domain. So this is j omega is frequent domain, j omega x. Okay, this one. Very similar way, discrete time cases. So we took a G transform of this guy 0.8 to the gamma to the n u sub n. Then pole is located here. Then is this is outside, region of convergence is outside, exterior, outside from the circle of the 0.8. And now the important thing is that the unit circle, in the case of gamma equal 1, when gamma equal 1, then g is e to the j omega. There's a digital frequencies represent e to the j omega. That represent magnitude is going to be 1 and angle is omega. So this is represent unit circle. So unit circle is kind of frequent domain. Okay. So digital frequency is a maximum is from 0 to pi. Let me okay. In continuous time cases, omega, it can be from 0 to infinity. Okay. So in analog domain, the frequency is from DC to the infinity. But in digital frequency, discrete time case, this omega is limited from 0 to pi. Okay, normally, the minus pi to pi. Okay, normally, okay, this is the same thing. So digital frequency is always in frequency domain. In analog domain, the frequency response is, this one is, go to the infinity. But in digital frequency, always to the pi. Okay, this is frequency is only inside of this guy. All right, so that's special you have to understand. Okay. Any question about this? I give you some kind of idea about the physical meaning of S domain Laplace transform and G domain G transform. Okay, let's exercise. So far it's okay?
Yeah, it's okay.
Okay, let's do, from now, in the case of Laplace transform, so we using, this guy, e to the minus 2t, that case is, we remember this is 1 over s plus 2. So 1 over s plus 2 is, inverse Laplace transform with this guy. Exactly the same way, okay? Exactly the same way, G transform. So this is a gamma, okay? Suppose gamma to the n, u sub n. Okay, so this is, this is a gamma here, for example. Okay, so if this guy is a backward, this one. So please remember this format. So G, over G minus gamma, something like that. Okay, in the case of the gamma to the n, u sub n, right side sequence. So please remember this formula, G over G minus gamma, okay? Something like that. So please remember that. So we're gonna use, instead of the summation, we're gonna use this guy, okay? So that this one is, okay, 0.8, because, we're gonna expand it, 0.8 to the n, u sub n. Okay, so this one already know. What is it? So G is G over G minus 0.8. Okay. Everybody follow me? Okay. All right. So the same thing. No different. Okay. Okay. What about this guy here? So this is shift. Okay. So let's take exactly the same way. Okay. This one is this starting. This is non-zero value starting from 1 to infinity. Okay, u sub n minus 1 is starting from 1 to infinity. Okay, so 1 to infinity, then 0.8 to the n minus 1. So this is 0.8 to the n minus 1. So this one is, this one here. Okay, this is same with 0.8 to the minus 1 and 0.8 to the n. Okay, exactly the same way. So, this one here, this one is the same with this guy here, and 0.8 to the n, 0.8 to n. But problem is we're starting from 1. So we're starting from 1. So this is 0, 1, 2, 3, 4. We're starting from 1. So we're going to make starting from 0, 0 here, and we need to eliminate n equals 0. So in the case of n equals 0, so this is n equals 0, 0.80, g to the 0 is 1. So we have to eliminate the minus. Okay, otherwise you can do this way. Okay, we can use this formula. Okay, this formula. Okay. This formula. Okay, using this formula. Okay, without this, you can do this way. Okay, you can do it like this. Just from here directly, 1 minus, actually, we have to do this is 1 over 0.8 and this one. And then 1 minus 0.8 and then 0.8. Okay, starting is 1. So this is 1 minus 0.8. Okay, g to the minus 1 or infinity. Oh, I'm sorry, this is g to the minus 1. Okay. All right, so starting from 1. Okay. So what I'm saying that this guy is 0.8 g to the minus 1 starting from 1. Okay, instead, okay? So you can do exactly same thing, no different, okay? No different.
So just
Okay.
to be clear, whenever you have it shifted where it's n-1, when you're coming down to the x of z, you're gonna always have a -1 after the 0.8 to the n, z to the negative n.
You know, this one, no, this one, first of all, okay, first of all, you need to change. This one is, you know, 0.8 to the -1 minus, still unstable. Still. Oh, this one is 0.8, -1 and 0.8 to the n. And so you need to you know, divide that, and you know, and then you can do, I should be able to, okay, now I can do. Okay, so this one, instead of this one here, and okay, first of all, 0.8 to the -1 and summation, and n from 1 to infinity, and 0.8 to the n, and g to the -n. Okay, so you need to notice about the starting point is not 0, is 1. So say instead of this guy here, all right, so you can do 1 over 0.8. Okay, so just directly closed form of 1 minus, for this one here, 1 minus 0.8, 0.8 g to the -1, and 0.8 g to the -1. Okay, and starting point is 1. Okay, this is starting point 1. Starting point is 1 here. So this is 1. Okay, minus, you know, this one is infinity. So this is reasonable convergence, this is equal to 0. So you can using this guy. Okay, so you can do like this. Okay. Otherwise, you can follow either way. This way, you can do this way, or you know, you can do this way. Okay. So either way, this way or this way. Okay, it's the same thing. Okay, no difference. Anybody understand?
A little bit like that last portion at the bottom. No, show the bottom thing that you, the bottom part of the slide, the equation.
This is 1 minus.
Oh no, the work that you have actually shown on the slide. Could you show all of it? You just took it off.
Okay, so this one, right?
Yeah, that one right there.
Yeah. So
So
this one is I using this instead of this one. Okay.
Yeah, and so
It doesn't matter.
can you put it back down there? I just had a question about that.
Yeah, I will do after I erase it. Okay, so this one is here. So this is, we know that g over g minus 0.8, and then this minus 1. So this is in a common term. So this is g minus 0.8, and then, you know, this is minus g minus 0.8. So actually gg cancel out, and this is 0.8. So 0.8 is canceled out.
Oh, so once you get common denominators, then it
Right.
Okay, yeah, that's what was tripping me up.
Okay, so you know, actually the this way. Okay. Okay, so this one here, common term, common. Okay, sometimes work, sometimes not work. Okay, all right. So this is common term is 1 over 0.8, and this is g minus 0.8, and g, okay, minus 1 times g, so g plus 0.8. Okay, so this is g cancel out, and then 0.8 cancel out. So this is this one. It's okay?
Yeah, no, that makes sense now.
Yeah, but as you know that, we always have to have a g over, g over g minus a. So to make the same form, g over minus a, then this is g to the minus 1. The g to the minus 1 times g is 1, so 1 here. So what does it mean is, we have, this is one delay. So one delay means, so later on we learn about the property of G transform. So one delay is, this is the meaning of one delay, okay?
So if you were going to ask this question on a quiz, for instance, does it matter the form that you answer it in? Like the first one was 1 over z minus 0.8, or you could have the very bottom where it's z to the negative 1 times z over z minus 0.8.
Yeah. If to using the table, I'm going to supply the table, G transform table. Then you can use this guy here, and then delay. Using property of G transform, the one delay. This one delay. So one delay is G to the minus 1. So for example, suppose you have a 2 delay. Okay, two here. Then instead of this one is a 2. You understand?
Yeah, no, I get it now.
Yeah.
I appreciate it. Yeah, no, it makes sense. It just
Yeah.
kind of have to kind of see it worked out.
Yeah, okay, because at this point, we did not learn about property of the G transform. So, inside of property of G transform, there is a time delay, okay, function, okay? Just like a Laplace transform. You can use it. All right. Okay, so now, what about this guy? So this is, if you're using property of G transform, that is the same thing of this guy. So G over G minus 0.8. And then now times, because of this G advance, so instead of the G minus 1, so this is just the G plus 1. So like this. That's a conclusion already. But using summation, okay, to using the formula, so we can we can change it to this y is this one is 0.8 times, okay, 0.8 to the n, okay, and then 0.8 is outside. Okay, 0.8 to the n here, we inside here, and this one. And also because of starting, the non-zero value region is starting from, the minus 1. So it's a minus 1. You can change it to plus 1. So plus 1, you can use this guy here. Or otherwise, you can use, the different formula, okay? But otherwise, you see one is n equals 0. But we have to include the n equal minus 1 case. So 0.8 to the 0.8 times g to the minus 1 to the 1, okay, to 1, add up. Because this case is, just starting from 0. This originally is starting from minus 1. So in the case of minus 1 cases, you have to using something that you have to include the 0.8 g to the minus 1. And then now, so you have to using n equal minus 1 case. Okay, so this one is 0.8 minus 1, and g to the minus 1 is positive g. So, you can do it like this. And then, this one is, we know that, this add up together. So you can common term. So, using common term, then you can do, g minus 0.8 and g squared. So this is same with this guy. This is, using property, we have this one, same thing here. Okay.
Now, compared to the the B exercise to the C exercise.
Uh-huh.
Whenever, so on the B exercise, you have it, you know, to the -1, and it's just, you know,
This one,
guess-
this one is 0.8, first of all.
I guess I'm
For the-
confused of why the Z,
Okay, this
right
is
under where you're writing. I'm confused why the
One-
Z is multiplied by the 0.8 to the -1.
this one here.
Yes.
This one. Okay, so this original. Okay, using the formula which I gave you, then 0.8 and g to the -1, and then now 0.8 g to the -1, and the starting point is -1. Okay, like that, and rest of it is zero. So if you arrange this guy here, this is same with this guy. Okay.
Okay, so you're just showing different ways to solve it.
Yeah, different way. So I think this may be more easy way. Okay, it doesn't matter anyway. You can do. Okay, so this is exercise. You can do like that from here. Okay, so this is starting from. Okay, please try by yourself. This. Oh, come on. Okay, so these two cases, please start by yourself. Okay. If you have a question later on, you can ask me. Okay, and then, okay, this is G transform. Okay, this is G transform, bilateral G transform. Okay, so x of n equal delta of n. So delta of n is only single value when n equals 0. So summation from n minus infinity to infinity, everything is 0 except n equals 0. So only one term n equals 0. So x of 0 is 1 here. G to the 0 is 1. So this is 1. Okay, so G transform of delta of n is 1. And then reasonable convergence is everywhere. Okay, because it's limited. And then no 0, no pole. Okay. What about this guy? Use of step function, G transform unit step function. With step function is the same thing, though this is actually one same with 1 to the n. Okay, gamma to the n. So we know that this is G over G. Gamma equal 1. So this is 1. It's very clear here, right? So same way you can find this. Okay, so this is same thing. So in this case, is 0 is G equals 0. Pole is G equal 1. And reasonable convergence is G is greater than gamma. So this is 1, 1. Okay, same. So this is on the unit, something like that. So far, it's okay. Any questions so far? Okay. Okay. What about this? It's only single value. Single value where? What is the location? N equal 1. So this is n equal 1. So only single value. Everything is 0 except n equal 1. So x over 1 is 1. Okay, and g to the minus n equal 1. So g to the minus 1. So this is 1 over g. So no 0. Okay, pole is g equals 0. Everywhere except the pole location, g equals 0. Okay, what about this one? This is single value and n equal minus 1. So n equal minus 1, this is x, n equal minus single value, x of minus 1 is 1. G to the minus positive 1, z. So this is z. So this case is, 0 is g equals 0. Pole is none. And everywhere except this, if this g is infinity, then it's going to go to the infinity. So except g equal infinity. This is two single value. Okay, so 1 to n equals 0, n equals 1. So we're going to plug in n equals 0. So n equals 0 is 1 times g to the 0 is 1, and n equals 1. So x of 1 is 1, g to the minus 1. So g to the minus 1. So this one here. So if you combine these together, then this is G plus 1 over G. So 0 is G equal minus 1, 4 is G equal 0. So everywhere except G equals 0. If G equals 0, G equals 0, then this is infinity, go to infinity. So except this one, except 4, okay? It's okay so far?
It's all right.
Okay, all right, so next time, I will give you, this one, starting from this point, and then also I will post the quiz number 9. Is it quiz number 9? Quiz number 10, right? Quiz number 10, right?
9.
Quiz number 10. Oh, quiz number 9 already, you have to submit. And then quiz number 10 is going to post Wednesday. Okay?
And you'll post the solutions for quiz 9 soon?
Yeah, before that, before Wednesday, I'm going to post it.